Hey, good morning, everyone. Welcome to the fourth of our digital twin webinar series here at Voxelmaps. My name is Brian Soliday. I'm a Chief Revenue Officer with Voxelmaps, and we want to welcome you today. As we go through the presentation today, if you have any questions, please use the question and answer pod at the bottom of your screen, or sometimes it'll be at the top of your screen. We're recording the session, and we'll be providing this to everyone after the event in the form of a guidebook with some really good information that we're going to talk about today. Please feel free to pass that along to any of your colleagues that couldn't make it today or that you think would find this presentation of value. For those of you that have participated in this webinar series, just an FYI, today's presentation is actually going to be the same presentation that we did back on Tuesday the 17th. You're more than welcome to participate. You'll probably pick up a couple more good nuggets in terms of the technology, et cetera. So you're more than welcome to sit in on it. Just wanted to let you know that it is the same presentation that we did on Tuesday the 17th. Okay, in terms of what we're going to talk about today, we're going to start off with a brief overview by Peter Atalla, our CEO of Voxelmaps, and the organization and the history behind the company. We're then going to talk a bit about maps for machine. It's a really different concept, I think, from what you're used to within the geospatial community. So it'll be interesting discussion there. Talk a bit about volumetric mapping and 4D volumetric mapping, which is really the baseline of the Voxelmap strategy. Talk a bit about the data collection network and the systems that we put in place to do data collection. Peter will also talk about our 100 Cities project, this DAS data set that we're putting together across the US. I'm going to talk about some of the industry use cases and the use of the technology across a wide variety of industries. And then we're going to share with you some information that we've pulled together that's out of the US Senate Infrastructure Bill, HR 3684. And it's really geared, this is what we pulled out that's geared towards geospatial. So if you're in geospatial, which I'm sure you are, otherwise you wouldn't be a part of this presentation, you'll find that really interesting. And then we'll close it out with a series of with questions. So with that, what I'd like to do is I'd like to hand it over to the Voxelmaps CEO and founder, Peter Atalla. Peter, it's yours.
Thank you very much, Brian. Hello, everybody. It's a pleasure to be here today and have the opportunity to tell you a little bit about what we're doing at Voxelmaps. So just to get started, I want to give a little bit of background to the company. So we're actually a spin out from a previous mapping company called NavMe. So NavMe was based in Europe, and NavMe was a navigation and mapping company. It mapped about 180 countries in the world. That's almost the whole world. Over a 10-year period, it was a huge project involving collecting about 7 billion kilometers of data and thousands of people. But about 5 years ago, NavMe had a division of the business that was really looking at the future of mapping and what that should be like. And that division essentially became Voxelmaps. So we spun out about 4.5 years ago. We have a head office in San Francisco, a number of regional offices across the US, and then we have a number of offices across the world as well. So we have Mexico City for Latin America, Nottingham in the UK, Porto in Portugal for the European market, and then Singapore and Australia and Sydney as well. We're currently about 350 people, growing pretty quickly, but that gives you an idea of the footprint. But in terms of what we do, everything is really around this concept of building maps for machines. So I want to start off by just explaining the difference between a human map and a machine map. So human maps, obviously, we're all familiar with them. These are the maps that are on our phones, that are in our cars, that we use on the web. And they're really around two use cases. The first one is navigating people to an address, whether that's a street or a building or a city. The second use case is really around visualization. And this is where you take some form of geodata and overlay it on top of a map. The majority of the data for human maps is 2D. There are some 3D elements, but it's still pretty small at the moment. And it's relatively low resolution. So we're talking about 1 to 3 meters in terms of accuracy. Now, if we look at machine maps, it's actually very different. Firstly, we're talking about true 3D models. So it's kind of beyond just a standard map. We're looking at a whole model of a given environment. And so we're analyzing everything that we see in the environment. So in cities, that can be everything from obviously the buildings and the roads, but the infrastructure, the telecoms, the utilities, all the way through in non-urban environments, the vegetation, land structures, land classification, for example. And we do this at a very high resolution, so 1 to 4 centimeters in terms of accuracy. And at that kind of resolution, it's not just about recognizing objects and where they are, but it's also about pulling back information about the objects, such as measurements and key attributes or features as well. And so when we talk about machines, this is everything from computer models and artificial intelligence to better understand cities and smart cities or in the environment, all the way through to new forms of autonomy, like autonomous vehicles or delivery robots, or things like AMRs, automated miniature robots as well. And there's a real requirement that this data isn't just outdoor, that's probably still the biggest use case, but also that there's indoor data, subterranean data, even ocean data can kind of exist within this map for machines. So I want to explain really how we do this, and the approach that we take is really around this concept of volumetric mapping. So I'm going to kind of dive into that a little bit. So the starting point is to explain really what the difference is between a volumetric map and a standard 3D map. So this is an example of a 3D map. This is from Google, but Apple has very similar maps, so does here, for example. And these are great maps for humans. Again, they look very pretty. They're a good visualization tool of the city, but they're actually pretty low resolution maps. So if we were to zoom into this map, you can see that we have very low resolution structures. Essentially, the buildings are just very basic mesh objects with a texture that's kind of wrapped around them. And so again, for a visualization tool, that's absolutely fine. But if we want to perform measurements, or if we want to know what was happening in terms of the interior of those structures, there's no information there. And one of the key things here is when you're looking at using meshes, meshes are just really focused on one aspect of physical matter, and that's the surface information. They're not so concerned with the interior information. And that's why a volumetric approach makes much more sense for certain use cases. For example, if you're imaging the body or imaging the brain, you're not modeling in a mesh. You'd model volumetrically because that interior information is actually really important. And so that's what we do. We create a model that uses a volumetric approach, which allows the surface to be mapped at very, very high resolutions, again, 1 to 4 centimeters. But in the same model, you have the ability then to fill in interior, even subterranean information. And that information can be collected either at the same time or at different times, and it will automatically drop into the model without any need for human involvement in terms of creating it. And the other aspect that we're adding onto this as well is this fourth dimension of time, which I'll tell you a little bit about, and this is around change detection as well. So how do we do this? So the approach is to use voxels, and I'm sure some of you know what voxels are. Voxel is just a 3D pixel, a volumetric pixel. Now, voxels by themselves are not new. They've been used for quite a while in different fields. I mentioned about the brain scanning, for example, that's one. They've been used in computer games. Minecraft is an example of a voxel rendered world. But in fact, what we do is use voxels in a particular way called a VOG, or a voxel occupancy grid. And so this kind of approach came out of robotics. And typically the use case would be that you have a small robot with some kind of laser scanner or 3D scanner on top. And it would go into a room and it would produce a very basic voxel occupancy grid, a 3D map of the environment so it can navigate its way around. So we took that concept, but we applied it to the entire planet. So this is a technology called an MRVOG, or a multi-resolutional voxel occupancy grid. So we took the Earth and we placed the giant megavoxel over the top of the Earth, and then this is full of multi-resolutional voxels. Now, these interior voxels within the megavoxel can be absolutely any size. For our purposes, we tend to use 8-meter voxels down to 1 centimeter voxels. Now, the grid goes straight through the planet. It's what we call an Earth-centered, Earth-fixed reference frame. So it starts at the center of the planet and works outwards. So wherever you're sat at the moment is actually full of these virtual voxels. Each voxel has a permanent position in space and a unique address, a machine address. But to start with, it's empty. There's no information in it. It's just a georeferencing system for 3D data. So what we need to do is validate the occupancy status of the voxel. Basically, is the voxel free space or is there something in it? So we do this mainly using LiDAR. So if the laser beam from the LiDAR passes through the voxel and it's not reflected off anything, then this is free space. But if it's reflected off a surface, then we collapse down to the smallest unit of the voxel, currently 1 centimeter. We label this as occupied. So in effect, what we're doing is we're etching out the matter of the planet. Now, by doing this, we create a global spatial database for this data. We don't view this 3D, 4D data just as some files you put into a viewer for doing visualization. We're really looking at how do we display, how do we process this data at a planetary level. And so the model that's been created here is real-time, which allows for real-time updates, particularly if things like 5G are available. It's persistent, which means it's always on, it's always available. You can do calculations across huge data sets. And it's designed to be planetary scale, handling thousands and thousands of petabytes in terms of scale. But it's not just the core platform itself. There's some other really nice features around using voxels in this way, which are much better than using points or meshes, particularly if you're looking at building out digital twins. So firstly, a voxel is a measurement unit. It's a 3D measurement unit. So by default, it's very easy to perform calculations within the space. Secondly, on the sides of the voxels, it's possible to put additional surface information on the sides of the voxels. So this can be things like camera information, so RGB values, but it could be hyperspectral imagery. It can be even things like radar. So with the voxels, we have the shape of things and the size of things. With the surface data, we have an aspect of color. And then we can use deep neural networks to look at these objects in 3D and recognize what they are. So this is a true 3D semantic segmentation at the voxel level. It's not just a 2D pixel-based approach. So the recognition is exceptionally high. But not only can it look in 3D at what's currently there, it has the ability to look what's been there in the past. So every voxel has an infinite number of time states. So there's this temporal data component. So the AI can look at what's here now, but also look at past data and compare and contrast the two. So really, this becomes a very powerful tool to do things like change detection. And then when you combine this with the permanent addressing, the spatial database, the ability to intelligently search, it's a really powerful platform. So I want to show you what this looks like. What does a digital twin look like using this technology? So this is a video taken from San Francisco. So this is the occupancy data in voxels by themselves. Then on the surface of the voxels, we have the camera data. And then all these pretty colors here, this is the AI recognizing features automatically and automatically vectorizing that data set. So then we have the flexibility to play around with the data. We can remove things we're not interested in, or export out the features that we are interested in, or put everything back and analyze it. Currently, the system's trained to recognize about 100 city objects. Very soon, we'll be up to about 200. And we're doing the same for the indoor environments as well. So the most common things that we'd expect to see in different indoor environments will automatically be recognized. We also have the ability to train the system to recognize custom objects that maybe we haven't trained it for as well. So once we've collected the data, we put it in the voxel model, we then have the Insights platform, which is a tool that we provide to customers to be able to go and analyze the data themselves, to export data out, and to even train and do things like virtual surveys. So in these screenshots here, anything that you see with a colorful color, a colorful line, or a colorful box, this is the AI performing a recognition event and a measurement event. And so it can run through the entire data set and at scale and pull back these features. And then giving you the ability to export into any platforms. So any kind of file type, or even via APIs to be able to connect into other platforms as well. Also from this interface, you have the ability to do things like virtual surveys. So this is just like a computer game. You can go in, walk around with the data, measure things yourselves, spin things around in 3D, and really get a feel for them as well. So you have a lot of flexibility. It also has the ability then to do this change detection that I mentioned. And this is just one example. Brian will talk to this as well. But in this illustration, what's happening is there's a pole that has been mapped before. So we've had multiple passes of data. And then there's been a new installation on the pole. And if the AI has been trained, it will actually recognize that installation and tell you what it is. But even if it hasn't been trained, it has the ability to recognize something has changed and flag it up with you. So this becomes, again, really interesting to use for this compliance angles, and Brian will talk about that as well. In addition to the tools that I've just shown you, there's some other useful interfaces. So all of the data can be available via the web, so you can use a web browser to access it, which makes it very easy to deploy within organizations. There's even things like the virtual reality versions as well, should people want to explore truly in 3D and immerse themselves. And there's some applications for AR as well, augmented reality. We also have the ability to provide tools to train the models, the AI networks themselves. Now, this is something typically we do for customers, but increasingly we're finding some customers want to do their own training. And so this video here just shows an example of this. This is a process we call annotation. So they're using a tool. This is a full 3D, it's not just 2D, and they can annotate automatically to train different networks to recognize different features. So here they're annotating trees, for example. So that kind of tool set can also be provided to the customers as well to use. So those are all the software side of things, but we want to talk now a little bit about the data collection and how we do that. So we have our own mobile mapping solutions, which are called Symbo, and these have really been designed to do large-scale collects. So one, they're cost efficient from a price perspective, but also they're really designed to be single-person operated. So the device is relatively small, fits in a Pelican case, and can be transported very easily around the country or around the world. And it takes about 10 minutes to do the initial install of the device, and about 5 minutes thereafter to put on and to take off. Once that's installed, you don't need to have a computer in the car. All of this is edge processing. So within this device, we have the LiDAR, which is obviously the laser scanner, the cameras, a high accuracy GPS and IMU, with the ability to have PPK and RTK as well. It has 5G connection as well, if it's available, as in if there's infrastructure around you to support that. And it was running NVIDIA graphics cards inside, which are doing the edge processing. So you have the flexibility here to do everything on the edge, and then that data can then be sent for the processing in terms of our infrastructure and our service. The only thing the operator needs is just an iPad. So the iPad is how you control that device. We have another version of the device which is coming out later, actually in September, the end of September. So this is pretty much a similar spec, but it has 2 LiDARs. And this just allows it to scan a little bit higher than the other version. So depending on the application, this also might be the version to use. Now, it's not just about the hardware. The hardware is one thing, but it's also how do you deploy this at scale and get efficiency for operators collecting this kind of data? And that starts with the mission planning. So we have a full back-end suite of technologies whereby you can take an area, that could be a city, a state, or even an entire country, and the system will break it down into daily mapping missions. And these are then tiles which can be sent and assigned to operators. So the operator would receive on their iPad the tile that they would have to go and map for that day. And this includes things like turn-by-turn directions, so it increases the efficiency of being able to do the collection. What the operator sees is this interface, and this is really easy to use. If everything is green, this is an overview of the box. It means everything is working really well, an overview of the Symbo. If there's any issues, then it's very easy to trouble fix. And in fact, these devices are remotely connected, so we can actually connect to them and fix any kind of calibration issues that somebody might be having. In addition, where you're driving, you see the trail of where you've driven. If everything in that trail is green, that's all fine. But if there's problems with the data, then it might go amber or red. And it's important that when that happens, we're giving the feedback immediately to the operator. So they have the ability to go back and redrive that area versus working out a couple of weeks later after post-production that you realize that there's some issues with the data, and then you have to go back and collect, which can be more costly. So this has really been designed with efficiency in mind and large-scale collection in mind. So really just summing up the benefits. Using the technology allows people and organizations to map much, much quicker than more traditional approaches. And again, it's not just about mapping at the resolutions we're collecting at, it's also about measuring and taking back features that are important around those assets. Because of the way that we deploy the technology and the ability to use single operator teams and to deploy very effectively, it really reduces the cost in terms of the operations. And of course, because what you're doing here primarily is building a full voxel map of everything that you see, it's not just one or two assets that you initially might be interested in, but you have the ability to then go into the data later on and pull back any additional features that you might need later. So just before Brian takes over and talks through some of the use cases, I just want to mention about an exciting project we've got on called the 100 Cities Data as a Service model. So this is where we're mapping currently at the moment 100 of the top metro areas in the US. We're doing all of the mapping ourselves, so that data will be available around Q2 next year, although we've already started for some cities, so it's already available in certain areas. And this includes the full 3D voxel map, so a full digital twin of the area, plus the things like the LiDAR point clouds, the high resolution imagery, the road networks, and all the features that are already extracted in terms of vectorized data. So we have the ability to deliver that data directly to you. So if that's of interest, you don't need to commission a project to go and do the mapping yourselves. This is data that can be used straight away. And this is something that we keep up to date on a regular basis. So these are just some examples of what the data looks like. This is obviously a zoomed out view. This is in San Jose. So mapping all of San Jose at this 1 centimeter resolution, so very, very granular data. And it's not just about the voxel data here, it's already all segmented as well. So the AI models have run across the whole data set, so you have full flexibility to pull out the things that you're interested in. And even in very complicated areas, so if you look at things like the transmission cables here, very dense in terms of the information, but again, all automatically recognized, vectorized, ready to go data. So if this is of interest at all, do feel free to reach out to Brian or myself. We'd love to share the list of cities in terms of what's going to be available and answer any questions you might have around those. So with that, I'd like to hand back over to Brian, and he'll take you through some of the use cases with customers that we work with. Thank you.
Thanks, Peter. All right. So what I'd like to do is talk a little bit about some real-world applications and use cases of the technology across a wide variety of industries. There are, pretty broad capabilities in terms of the use of the 4D volumetric data model that we have. So it's, pretty broad, as I mentioned. So it's, the smart cities, it's vegetation encroachment and utilities, it's, street furniture inventory on the transportation side, or right-of-way, public works, simulation planning, management, or collection of the distribution or transmission networks as well. So pretty broad capabilities in terms of where our customers today are using the technology. One of the use cases is that we did in the past was a mapping of traffic signs. So in this case, the end customer was a major navigation company, and what we did was we went out and drove significant number of miles of roads, and then did an extraction of all the signs within the right-of-way. So we then also created on each one of those objects what type of sign it was, what the text was on it, etc. But 7 million signs were mapped. So a pretty large project. So it just kind of tells you, we can scale pretty significantly to support a wide variety of applications. Another one is installation compliance. So you think about this whole 4D model. In this case, we had a database of a city, and then we went and drove again and collected the data. And then we could do change detection on what had happened in that environment, maybe new sign in the right of way, new poles, new trees were planted, etc. And look at how that maps against the local government laws and regulations, whether or not they're in compliance, etc. And again, because of the automated feature extraction or feature recognition extraction, and then the automated measurements, it's pretty easy task to do that compliance. In terms of the city infrastructure, there's pretty broad capabilities in terms of the use cases that we can support. So it's it's the local DOTs, it's public works, it's city planning. In the upper right here, this happens to be an area that we collected, but the customer actually had some lower resolution data of buildings, digital twins of the building. So we drove and then inserted their models into the voxel structure. So you know, we can utilize a wide variety of data sources. So we're really, in terms of the data itself, we're really source agnostic. Road network mapping. So in this case, it was for a data collection we did for a major automotive company. What they were looking for was an HD map, a high definition map for autonomous vehicles. And so we went and collected a vast number of miles of roads, you know, extracted full roadway models, traffic signs, striping, you know, localization objects, etc. So a wide variety of capabilities. Lots of talk too about smart cities, and so smart cities includes, you know, things like you know, LiDAR in vehicles as well, the whole autonomous vehicle and vehicle to everything, the V2X concept. So you know, you can use LiDAR to monitor traffic. The good thing is it's both night and day, so it doesn't need to be light out for LiDAR to work. You can do car counts. You know, local governments can do car counts and see where they're having you know, busy intersections. They can also identify vehicle types to see, you know, if they've got more panel trucks moving through areas than they think they do, and really help cities understand where they have issues and why, and then they can implement implement programs to help solve that. You know, you could also use it in the area of like security management or pedestrian monitoring. So again, in the smart cities world, there's lots of different areas where the technology can be used. And the digital twin concept that we're talking about today, you know, digital twins within the city can be used for a wide variety of things. So disaster management or response and recovery, city mapping, construction monitoring. You know, there's this whole push towards digital construction. You know, looking at infrastructure like bridges and roadways, identification of issues with those. We'll talk a little bit about that because there's lots of money in the infrastructure bill specifically for that, for you know, monitoring the infrastructure as well as the digital construction. So, and then detecting these urban environmental changes as well. So looking at, you know, the amount of vegetation in the downtown urban corridor. Again, with that 4D, you know, that fourth dimension of time, being able to go back and look and see where changes have occurred across the environment. This is an example use case of an indoor visual positioning system that we did for automated miniature robots. And I'll start this, but Peter, if you'd like to give a brief overview of what we're looking at first.
Sure. So if you just pause it one moment, Brian, just while I explain. So
yep.
Essentially, we've got three screens here. The bottom screen is a voxel map of the interior space of an office. So it's the same technology, obviously, that we use for mapping outside of the building, but taken inside to do the inside mapping. So this voxel map has been pre-created, and then it's been loaded on an AMR, an automated miniature robot. The two screens that you can see at the top, these are the views from the robot itself. So the first one is on the left is the RGB value camera. And this is just showing where the robot is and what it's looking at. The one on the right will actually show you that it's a depth camera as well. Will show you the recognition events. So what's happening here is the robot is taking its local copy of the voxel map, comparing it to what it sees around it, what it senses around it, recognizing voxels, and then triangulating its position to centimeter level accuracy. So this kind of use case is around robots indoors, particularly in warehouses, for example. So Brian, if you just play the video, please. So the starting point is there's going to be a little bit of a calibration. So it's just calibrating itself now. So it's just recognizing it. You'll see now in the top right-hand side, this is kind of a live stream of what's going on. And so all of these purple voxels and green voxels that you see there are the recognition events. So this is it recognizing different voxels and clusters of voxels and triangulating its position. You can see here in the top left, this is the view from the robot app as it's been taken through the environment. And you can see then in the bottom, in terms of the voxel map, it's updating its position in real time. And so what's really interesting with this as well, not only is it doing this very well on the X and Y axis, but also on the Z axis as well. And so being able to look at those kind of changes to centimeter level precision as well. So you'll see in a moment, it's going up the stairs here and actually having that change reflected. So again, just an idea of how the same technology, the same map and model is used to power these kind of robots and machines.
All right, cool. Thanks, Peter.
No problem.
So that just gave you an understanding of where it could be used both internally, and then we've been talking a lot about the external. So again, what's really nice about the voxel structure is that I have an external digital twin. I can just plop in that internal information without having to regenerate a mesh like I have to do with traditional LiDAR LiDAR and with LiDAR storage. We've seen lots of interest in the utility side of things. So in terms of utility asset inventory. So in this case, it's aerial data that was collected using a manned aircraft, right? And so again, as I mentioned earlier, we're really data source agnostic. So it could be aerial LiDAR, it could be UAS LiDAR, it could be mobile LiDAR from your system or from ours. So a wide variety. In this case, we then process the customer capture content. We use the AI, or artificial intelligence, machine learning based automated feature extraction, recognition and extraction to identify the different features in here, and then validated the assets against an existing geospatial database. There's also lots of interest in performing joint use audits. So in the utility industry, you have someone who, a pole owner, many times it's a utility, many times it's the local governments that own it. But people can attach to that and they want to know who's attached and where the attachments take place. So this is really support for the field inventory of pole attachments, whether it's electrical, comms, fiber, really any sort of, it could be a light attachment as well. And then they use this to update the records for location ownership and the assets on each pole, and then identification of violations, NESC violations as well. One of the probably most important areas right now, based on some activities with utility caused fires, is the whole vegetation management and encroachment. So, what we do is we can drive these areas. So you can see at the top, there's an image of the area. The next image is the voxels that have been colorized using the RGB values. And I will say, a lot of the data that we show is when we show imagery, right, is that middle sort of an image. And I get feedback from people saying, how come your data is so pixelated? Well, it's because we're creating what Peter talked about earlier, maps for machines, right? So for me personally, the top image looks good, right? To the machine, that middle image is what it used to perform extremely valuable calculations for us. So in this case, we drove an area, a city, did all the data processing, used the AI ML backend system, the VIP system that Peter talked about to do the extraction. And then what we did was we then took the conductor lines that we had identified and created buffers around them. So at different distances, looking for vegetation encroachment within different distances from those conductor lines. And then you can perform quantification of that as well. So if I look at an entire area here, you can see, the issues are the bright red spots of the vegetation where we have conductor lines crossing in very close proximity to the vegetation. But what again, because these are 4D volumetric entities, the voxels themselves, I can then go back and extract and say, okay, I want to know everything that's within a half a meter, basically a foot and a half from any of my conductor lines, identify those voxels, and then here on the lower right, generate a report for me. I want to know how much in terms of total vegetation needs to be removed off a given circuit. Okay, and so from the utility, it's a good management tool to understand what needs to happen. And actually, from the contractor, it's a really valuable tool so they can know how much vegetation when they roll a truck, how much vegetation is going to be required. And so you can take that, it's just a simple CSV file. They could take that as a utility and pipe that into their work order management system and use it to roll the trucks to the right location. And then they know how much vegetation needs to be cut, and they know what sort of a truck they need in terms of how much height they need to get out of a bucket to remove that veg. There's also great interest in the use of the technology for street and roadway lighting. So, there's lots of activity around LED replacement across the country. And so being able to create an inventory of all your lighting assets is pretty important. And then, using the VIP system to be able to identify and classify all the lighting types. So, Cobra versus the single versus double arm, things such as that. And then extract those assets in a vectorized format and export that, into like a shape file for consumption by your ArcGIS system. So pretty powerful tools. In the telecommunications space, so this is a picture you've seen earlier in the presentation, but in this case, we had a customer that in an area where we had previously collected. So we had collected this city in San Francisco. So we had it in our database. What they were interested in was looking at validation of their contractors' work orders, validating whether the contractor placed the right asset, the right 5G antenna on the right pole, right? So in this case, you can see, we have two poles close together. They just wanted to make sure that it was on the right pole. So we went through and trained the VIP system to be able to capture those assets, those 5G antennas, and then identify them and give a location as well. So it gave them a really solid database. And in this case, all the customer really wanted was, give me the XYZ location of that asset, the pole, and the particular 5G antenna location as well. So they didn't need all the data, up and down the street. They just wanted to know where things had changed. We've also done some interesting work in the area of 5G signal mapping and signal propagation and attenuation. So in this case, what we did was we drove the whole city of Chicago and built a digital twin. And in this case, we built the digital twins of the buildings, and then on some of the facilities of this particular customer, we went internal to their facility and did data collection as well. So we created both external and internal digital twins of their properties, and then we took their signal locations, their 5G assets in the field, and then ran a signal propagation model and tried to determine, where they had gaps within their 5G coverage within this area, both externally and then inside of their building, so they could actually, walk the halls using our model, walk the halls of their building and see where they had or did not have solid 5G coverage. So in that middle image there, in the middle of the three images, you can see these floating voxels. Those are actually voxels of the signal, right? So it shows, the level of that there is coverage and the level of coverage. There's also lots of interest in the area of automated HD map creation for autonomous vehicles. So in this case, collecting data for consumption into a high definition map. But you think about a DOT in being able to extract, edge of pavement, right? And extract striping and street furniture like guardrails, et cetera, or cables, right? Cabling in the center median. And then being able to, in the right of way, extract things like signs, right? And measure those signs to know that they're in compliance, whether or not, the signs are too large for that particular right of way. So, I mean, that's in the upper left too, you can see these are, recognition events and being able to capture all sorts of information and then auto vectorize those for consumption in your GIS. You know, there's lots of autonomous vehicle capability or interest. You know, one thing that that we're looking at as well is putting together a constant collection network. So being able to outfit fleets of vehicles that travel routes on a regular basis with both LiDAR and camera. So it wouldn't be like our Symbo system, but it would be a you know, much simpler data collection network with a single camera, single LiDAR, but being able to communicate that information to a central repository to update the road network, what's happening on the roads on a regular basis. You know, especially in the area like emergency management stuff. Really popular for transportation planning, and then the whole smart parking concept with you know, vehicle to everything. You know, in the relative near future, we're going to see, you know, everybody's vehicle talking to every other vehicle. It's going to be it's going to take a lot more 5G resources out there to be able to do that, mind you, but it will be happening. And you know, something simple like parking management. So as soon as I pull out of a parking spot at Home Depot, you know, it identifies that as an open slot for others in the local area that are navigating to Home Depot. So this is an example use case of a pilot project that we recently did, just to talk about the current process, really, to set the stage here. So the current process to create a high definition map is, you know, data collection. So we go out, we do data collection using our Symbo system, and then the mobile mapping sensors, you know, the LiDAR and the high definition cameras. And then those hard disk drives are physically shipped to a data center where, you know, we perform the raw data processing, all the data corrections, if there's any PPK, you know, sorts of corrections, and then create, you know, this voxel data merging capability. And then within the VIP system, being able to do using the AI tools to do feature extraction and then auto vectorization and create that high definition map, then deliver that to the end customer, and then they would then provide those updated maps for display in their vehicles. Now, this is about, you know, a 4 to 6 week process, which in the grand scheme of things, that's pretty quick, right? But in this case, customer was looking at how do we get near real-time updates of HD maps. So we just did a project with Verizon Wireless as well as Amazon Web Services. So this project was actually presented, Peter was a part of the team presenting that at the Mobile World Congress in Barcelona last month. And so, again, we used the same data collection devices, you know, the Symbo, except this time we have a Wi-Fi antenna on the Symbo. So at the time of collection, we were delivering the data. We were really focused on the LiDAR side for the 3D. So we delivered the LiDAR data across Verizon's 5G edge network. And then AWS Wavelength is actually an AWS instance that sits inside of the telecommunications facility. So it goes across the network instead of having to bounce across the internet to an AWS instance. It's right there at the telecommunications, right at the edge of that 5G. So we took that, created a 3D model, did the extraction of the data, and then delivered that again back across Verizon's 5G back to the vehicle for a display of the 3D model in the vehicle with an average turnaround time of 15 seconds. So pretty significant, right? So we went from about 6 weeks to about average of 15 seconds. So you know, they're really looking at the telecommunications company looking at enabling this 5G bandwidth and mobile edge computing, the Mac, for really super low latency computing applications, which autonomous vehicles, you know, if they're going to really be autonomous, are going to require this in the future. So pretty exciting. And I can show you really quick. I'm not going to play the whole video, but this just shows you the amount of data that we are collecting. So this is just showing in 15-second blocks, basically the data. Our team was out driving, and then the data was being again uploaded, and then processed and delivered back every 15, within a 15-second block. Pretty exciting. All right, so that gives you a pretty broad understanding of the different use cases where the technology can be used, and it is really broad. In fact, one area that I didn't talk about is in the area of natural resources. So there's an initiative called the Earth Archive, and we're the technology running the Earth Archive in terms of their consumption of a global data set to build a digital twin of the planet for natural resource applications. Oops. So let's talk about what's happening on the Hill. So this U.S. Senate infrastructure bill just got passed by the House. It's HR 3684. The interesting thing about this is it is a significant amount of money. And this Infrastructure Act it's authorized funds for federal aid highways, highway safety, transit programs, and for other purposes. So the full text of HR 3684 is about 2,702 pages. If you'd like to review that, feel free to do so. But what we've done is we reviewed it and tried to pull out some critical components of it to share with you, and that's kind of what I want to do today. So it's approximately 1.2 trillion over 8 years. I heard the number 1.3 a couple nights ago, but this kind of breaks down in terms of where the money's being spent. So roads and bridges and major projects, $109 billion. Electric vehicle infrastructure, 7.5. Electric buses and transit, 7.5. Airports, if you're involved in airports at all, 25 billion. Broadband infrastructure, so getting broadband across the entire country at an investment, pretty significant investment. Power infrastructure, so utilities. So it's not just, when I think of infrastructure of what they're working on, everybody's thinking transportation, right? Roads and bridges, highways, things that are crumbling, right? But it also includes the power infrastructure as well, and making sure the grid is up and running at all times. And then the infrastructure resilience. So you see, it's a lot of it is geospatial oriented, right? So it's good for us in the geospatial community. So what's interesting is that you can search the document and look for specific things, which we did. So you look for digital twin and digital cities or virtual reality or augmented reality, and those are probably too specific. But the bill was seems to be well written, and the bill itself, the outline provides a pathway to those goals, fulfilling the goals of like digital twin and digital cities. And the bill, outlines everything else really well, but doesn't necessarily specifically identify those. But if you read between the lines, it really, that's what they're focusing on. So digital construction is something that's, a really big focus of it. And so with all this infrastructure building going on that they expect to go on based on this. So, our view is, the surest way to the whole digital construction is to be, have data in a very rich 3D environment for design and construction, and really that whole infrastructure lifecycle. And what we really feel is that the bill may be really the catalyst for many entities to really take that full 3D and 4D plunge. So, Voxel, just in a quick review. So Peter gave us an overview of Voxelmaps and the history of the organization and where we came from and where we're going. Talked a bit about the concept of maps for machines, which really is it's a different concept for a lot of people, and it's really where our focus is. We spent some time on the volumetric mapping and talking about the whole 4D volumetric mapping that Voxelmaps and the technology we've developed and what we're bringing to market, and talked some about our Symbo and the data collection capabilities and the back-end engines that we have, and then mentioned the 100 cities, the DAS data set that we're organizing across the country and doing a pretty robust collection, very robust, I should say, collection. I then spent some time on discussing industry use cases, and then finished up with talking about this infrastructure bill. And I will say this, what we've done is we put together a white paper that really pulls out a lot of the geospatial components of this infrastructure bill. And that's a part of this guidebook that we'll be sending out to you. So it's about 8 or 9 pages of stuff that I think you're going to find really valuable. And so I hope you spend the time to look at it and see where your organization can leverage what's happening in this infrastructure bill to your benefit, and maybe think about how Voxelmaps can help you in that implementation. So with that, I'd like to open it up to questions. So somebody said, please send a copy of the white paper. No doubt, everybody on this call is going to get a copy of the white paper, no doubt about it. And so again, as I mentioned, it's a guidebook that has links to all of our webinars, as well as the white paper for the infrastructure bill as well. So here's a question, Peter. So what countries do you operate in?
So we're live in, 26 countries at the moment. I still say that North America is still the biggest, so US and Canada in terms of what we do, but it's extensively across Europe, also parts of Asia, so Singapore, Hong Kong, Australia, that we're doing collection in as well.
Okay, all right. Many of the images that we showed had cars and pedestrians removed, especially those involving transportation. So what's our process to remove that, what some people call noise?
Yeah, sure. No, good question. So actually the deep neural networks that we use, that we train to recognize objects that we're interested in, also do the same thing for the ones we're not interested in. So it's actually a deep neural network approach. So the artificial intelligence removes those voxels that relate to people, cars, cyclists, pets, etc., and remove those from the scenes.
Okay, thanks. So how much processing are we doing on the edge in the vehicle, and what data are we processing there?
Yeah, so what's actually happening on the edge is what we call sensor fusion. So it's taking the streams of information from the LiDAR sensor, from the cameras, from the GPS, etc., and merging all that together into what we call a voxel stream. And so all of that processing is done on the edge. And then the AI extraction is happening in post-processing, which is automated in our private cloud.
Okay, all right. What's the accuracy of the voxel data?
So there's 2 aspects there. So absolute positional accuracy on the planet is 10 centimeters or less. That's kind of what we guarantee. And then the relative accuracy or resolution really is around 1 to 4 centimeters. Both are totally achievable, just depends on the use case. So in most situations now we're using 1 centimeter.
Yeah. Why does AI work better with voxels?
So it's more the fact that it's looking in 3D rather than in 2D. So you can use semantic segmentation on a 2D image, a flat image, and that's pixel based. And so you would annotate various pixels, in terms of recognizing features there. But when you're looking at doing AI in 3D, you have 2 opportunities really. One, you do it as points, or you do it as voxels. And so combining it with 3D, doing it with the voxels, the fact you can see the object all the way around makes a huge difference in terms of the recognition for the vast majority of features.
All right. Here's a good question. Do you have pre-trained models ready for feature extraction?
Yeah, absolutely. So as I mentioned, we've currently trained the system to recognize 100 different features or assets in city data at the moment. We're in a constant process of training and annotating more data. So we'll be up to about 200 pretty soon. And we're already doing the same thing for the indoor data set as well. It's not released yet, but that's already in beta as we speak. So, yeah, we have pre-trained networks, and we can also train the networks on custom features for people and customers.
Right, that's what I was going to say. We have the ability to train if you have some unique, roadway features or utility assets that are unique. The system can be trained to extract that out as well.
100%, yeah.
Can the data be consumed natively in a CAD environment?
Yes. So, well, two things with that. Typically in a CAD environment, we export the data out into a different format. So you wouldn't want to ingest the voxels into the CAD. It probably wouldn't be able to handle them. But we have connections. We support different formats so that you can export into that format and have that automatically then within the CAD applications.
All right. Here's one. So basically, if I have my own data, or I collect data via UAS LiDAR, and I want Voxelmaps to drive the same area, can we merge those data sets?
Yeah. So in fact, we do that quite a lot. A few weeks ago, we just finished scanning San Francisco by the air as well. So it wasn't actually UAV, it was using a helicopter with an aerial LiDAR and camera system. And then we took that data, we merged that into the Voxel model with the mobile collector that we're doing with our sensors as well. So yeah, totally possible. We need to know some calibration parameters and obviously the devices that are being used. But yes, that's easy to do.
Okay, all right. Here's another question. What kind of sensors and platforms are you utilizing to capture coastal and ports data? And are there other challenges you can comment on working near the land-water boundary?
That's a good one. And in truth, I'd have to say that, it's a relatively new area for us in terms of looking at coastal and kind of doing some of the bathymetric stuff that we're doing. So we do have projects doing that. Again, we've just done one in San Francisco where we've scanned the kind of the water boundary as well. So we have, I don't know to what depth we've scanned, but we have that information. We're modeling it at the moment. So definitely a slightly different use case and consideration. We also have worked with partners that provided that data to us, and we've modeled it in the Voxel world as well. So I have to say I'm probably not the best person to answer that question just yet, but definitely I can connect you with our guys who actually are working on that project, and they can fill you in on the details there.
Yeah, I mean, there's a wide variety of platforms that can identify and collect the bathy LiDAR. So in a previous life, we were collecting using UAS bathy, but airborne bathy as well is becoming pretty popular. So. All right. I think that's it. That's all the questions. We surely appreciate everybody participating. As I mentioned, we're going to be sending out a copy of the guidebook, which has a link to all the webinars, as well as the infrastructure bill information in there as well. So with that, we'd like to again thank you for your time, your participation in this webinar series, and hope to be talking to you all soon. Thanks.
Thank you, everyone.